Hello everyone. Let's move on to question 6 of the mock test for CET. Let's read the question quickly. The question says that we have two wires of same length and they are shaped into a square and a two-looped coil. If they exhibit the same magnetic moment when current flows through them, then what is asked is what would be the ratio of the current flowing through both these wires. So the options given to us are 2:pi, pi is to root 2, pi is to 4 and 4 is to pi, and the correct answer for this question is 2:pi. So let's find out together why exactly the answer is 2:pi. So let's begin. The first thing told to us is that we have two wires of length L, so let's take two wires of length L. The first wire is shaped into a square shaped coil, as you can see. The second one is then molded into a two-looped coil. So I had two wires of length L and now I have molded them into a square-shaped and a two-looped coil. Now once I have this, the first thing to understand in this sum is the hint that I will now give you. The hint is that the length of the wire is equal to the perimeter of the figure. You had a wire of length L and this length L is now made into a wire which is square shaped, which means that the side of this square must be L by 4. And this is obvious because if I add up the L by 4s for all the sides of this figure, then I can write L by 4 plus L by 4 plus L by 4 plus L by 4, and that will give me L, which it should, because I have used that wire L to make this figure which is a square. In the same way, I can remember that I used the same wire of length L into making this two-looped coil, and therefore the circumference of each of these loops must be L by 2. So the outer loop must be having a circumference of L by 2 and the inner loop will also have a circumference L by 2, because totally together they should have L by 2 plus L by 2, which is L, the original length of the wire that I used. Of course, if you are thinking, how can they both have the same circumference when one is inside and one is outside? Then remember that I have drawn a 2D figure of a 3D object. A two-looped coil is actually a 3D object where one loop is in the front and the other one is behind it. But since this image is for representational purposes only, you have been given a figure in this way. So remember, these are actually two loops, one behind the other. Now once we have got that out of the way, we are going to use the information we just found to find the area of each figure. So beginning with the area of a square, recall the area of a square is nothing but side square, and therefore since my side in this case is L by 4, I'm going to bring it down and find the area of the square, which is L by 4 the whole square, which is L square by 16. So I have the area of the square is L square by 16. I'm going to do the same thing for my two-looped coil, that's find the area. But to find the area of a circle, which each of these loops are, I need the radius. So the first thing I want to do is find the radius. Now to do that, I make use of the information that the circumference of each loop is L by 2, and since circumference is nothing but 2 pi r, I say 2 pi r is equal to L by 2, and this gives me the value of the radius, and the r comes out to be L by 4 pi. Now using this quantity r is equal to L by 4 pi, now I can find the area of each coil, which is nothing but a circle, and therefore I apply the formula for the area of a circle, which is pi r square. And for this formula, I'm going to replace the r with the value I have found. That is, instead of r, I'm going to write L by 4 pi and I'm going to square this. It gives me the area of each coil, which is nothing but L square by 16 pi. So I have area of each coil as L square by 16 pi. Now all this begs the question, why am I finding the area of each of these figures? So to remind you why I'm finding the area of these figures, I'm going to go back to the question. But first, I'm going to need both these areas, so I'm going to save this as given in my figure. So this is the information we're going to need. Now let's go back to the question and ask, why did I need to find the area of each of these figures? Now the question says that I have to find the ratio of current flowing through both the shapes of the coils. So to answer that question, I'm going to use the information that both of them have the same magnetic moment. So I say m square is equal to m coil. Now here comes the best part. If you recall, magnetic moment is nothing but the product of current into area. In case of a square, it's a simple product. Current passing through the square into area of the square. But in case of a two-looped coil, it would mean that I have to keep in mind both the areas. That is, I have to keep in mind the area of the first coil plus the area of the second coil. And therefore, in general, if I have a figure which has n number of coils or n number of turns, I'm going to write down the magnetic moment as NIA, where n is the number of turns or number of coils, I is the current passing through the entire coil, and A is the area of each coil. Once I have this, I will rearrange and I get I square upon I coil is equal to NA coil upon A square. And now I will replace these A coil and A square by the quantities that I found. So now you know why I needed to find the areas of both the shapes. So once I have this, I'm going to replace the area of the coil with L square by 16 pi. So I'm going to bring it down here. And similarly, I'm going to replace the area of a square with L square by 16. I bring that down as well. And this gives me the expression that I need. Remember, I have used 2 for N because I have 2 coils in this 2-looped coil. Now, if I calculate what I need, I will cut out L square by 16 from up and down, and what remains is nothing but 2 by pi, and this gives me the answer. That is, the ratio of current flowing through both the wires is 2:pi. Thank you for watching.